In this online lecture, we're going to be talking about the nomenclature of coordination compounds, so how we name coordination compounds. And through this process, through talking about some of these coordination compounds, hopefully we'll become a little bit more familiar with transition metal compounds and ligands. Last week, we discussed, we introduced different terms. We introduced what coordination compounds are, what coordination numbers are, geometry, etc. So that's what we did last week. So we're going to continue on discussing coordination compounds this week, but the first thing that we need to talk about is how we name coordination compounds. He said, I thought you said the chemical composition for water was H2O. When we're communicating about chemistry, we have to make sure that our audience or other chemists know what we're talking about. So that's why it's so important for us to have a standard way of communicating the names of coordination compounds. Okay, so let's just jump right in and talk about the rules for naming coordination compounds. I thought I would use this example. We talked about thiosulfate, sodium thiosulfate, that's a fixer in silver photography. It removes unreacted silver from photo paper so that you can fix your image. So we're going to go ahead and talk about the rules for naming coordination compounds with this context. So the first thing that you want to do when determining the name for a coordination compound is determining the oxidation state of the transition metal. So in this case, silver, for the coordination compound. And another way of saying oxidation state is just the charge. What is the charge? And there's an easy way to do that. You simply take the total charge, the charge of the complex, and you subtract out the charge of the ligands, and you'll get the charge of the metal. The idea here, another way of thinking about this is that, so you're just solving for the charge of the metal by subtracting the charge of the ligands from both sides. So we can do that here. So thiosulfate, this is thiosulfate right here. So thiosulfate has a charge of -2. In this complex, we have 2 thiosulfates. So the charge of our metal is going to be equal to the total charge of the complex, which is -3, minus 2 times the charge of our ligand. We've got 2 of them, so it's going to be 2 times -2. So we get the charge of our metal is +1. Okay, so that's the first step that you want to do, is you want to determine the charge of the metal. So we know that it's Ag+. Okay, now when naming a coordination compound, if it's not an ion, this one's an ion, but if it's a compound so that it has a counter ion, and we could have counter ions, so we could assume that we have, say, 3 sodiums as our counter ion, because it's a -3 charge for this complex. So we would need a +3 charge to balance it. So you would name the cation first and then the anion. So in this case, we would name our cation, which is sodium, leave a space for our complex ion, which is our anion. For the coordination complex, in this case, it's second, but here are the rules for the coordination complex. You list your ligands alphabetically with the appropriate prefixes. So you list those first, then you name the metal, followed by the oxidation state. And like I mentioned here, you want to include a space between the counter ion and the complex ion. You say sodium, and we have 2 ligands. When it's an anion, it's called thiosulfate. When it becomes a ligand, it becomes thiosulfato. It would be called sodium, and we've got 2 thiosulfatos, so we would say dithiosulfato. Next, we name the metal. And here it's silver. And in a few minutes, I'm going to show you that there's some different rules. Anytime your complex ion is an anion, the metal needs to end in ATE. But silver also has a special name. Its special name is argentate. And then you want to include the oxidation number in parentheses. Okay, so that's how you would name this coordination compound. Okay, so here's the rules for naming ligands specifically. So anionic ligands end in O, so you remove the IDE and then you add an O. So fluoride becomes fluoro, chloride becomes chloro. And then neutral ligands are named the same as their neutral molecule typically, like ethylene is still ethylene, but there are 4 ligands that have special names. Aqua for water, amine for ammonia, carbonyl for carbon monoxide, and nitrosyl for nitrogen monoxide. And then the last thing we need to mention are ambidentate ligands. So this is an ambidentate ligand, meaning that it can bind from 2 different binding sites. So if it binds from the S, it's a different compound than if it binds from the nitrogen. So you need to include how it's binding in the name. So here we say S-thiocyanato if it's bound on the sulfur side to the metal, or N-thiocyanato if it's bound on the nitrogen side. Table of different ligands. It's from the Rogers textbook. When you're naming your ligands in your coordination compound, you need to include the number of each ligand with an appropriate prefix. So you use di if you have 2. So the example that we talked about, the thiosulfate silver complex, you say di-thiosulfato. Tri is for 3, tetra is for 4, penta for 5, and hexa for 6. So these simple prefixes you use for all monoatomic ligands and polyatomic ligands with short names. So even thiosulfato would be considered a short name. Or neutral ligands that have special names like aqua, amine, carbonyl, nitrosyl, you're still going to use di, tri, tetra, penta, hexa. But if you have a more complicated ligand that has di in the name, so one of the ligands that we're going to be talking about quite a bit is ethylene diamine. And you'll notice that ethylene diamine has di, it has this di prefix to indicate that there's 2 amines right in the name of the ligand. So we can't use di as a prefix for ethylene diamine because it would get really confusing. So for these more complicated ligands, we need to use bis, tris, tetrakis, pentakis, and hexakis. So any ligands that contain a prefix, you're going to want to use bis, tris, tetrakis, or neutral ligands that do not have special names, such as methylamine. And I often will use bis, tris, tetrakis for pretty much all bi and multidentate ligands, so oxalato, glycinato, etc. So the prefix and the order of the ligands is based alphabetically. The prefixes do not determine the alphabetical order. The actual name of the ligands do. So tetraamine would come before dichloro. This is what I was mentioning before. If your complex is an anion, the suffix ate is added to the metal. So platinum becomes platinate. So you get rid of the for a lot of them, like chromium becomes chromate. But there are a few metals with special names. Iron is called ferrate, copper is cuprate, lead is plumbate, silver is argentate, gold is aurate, and tin is stannate. Only when the complex ion is an anion. If it's a cation, then you just use the regular name, like silver 1. The last thing you do in the name of the compound is the oxidation state of the metal is given as a Roman numeral in parentheses. But I like to determine this first, even though it's the last thing that we include in the name. It's just a helpful thing to do before you start naming the entire compound. Cobalt. Now the overall charge is +3. All of these ammonias or amine ligands are neutral. So this is cobalt 3+. We've got 6 amines, so hexa, amine, cobalt 3, and then I'd leave a space, and then I would name my anion, which is chloride. And something that you might notice here is that I did not use a prefix for chloride, and that's because chloride always has the same oxidation number. Chloride always has a -1 charge. So as long as you know the charge of your complex ion, the complex ion, you have to give more information because transition metals can have multiple oxidation states. With this name, hexaamine cobalt 3 chloride, I know that this is a +3 charge, and this anion must have a -3 charge, so I know that there's going to be 3 chloride anions countering as counterions, balancing that charge. I wanted to go through a few more examples. In this case, the cation is is the complex ion is the cation. So the first thing we want to do is determine the oxidation state of chromium. We've got 3 chloride anions, so total charge of -3. So that means that the charge for the complex ion must be +3. Remember that our charge of our metal plus the charge of our ligands is equal to the total charge on the complex ion. So we can solve for the charge of the metal by saying 3 minus the charge of the ligands, which in this case they're all neutral, is going to be equal to the charge of the metal. So it's just +3. So this is chromium 3. Okay, amine comes before aqua alphabetically. So if we're going to name this, it would simply be triamine triaqua chromium 3 chloride. Here's another example. This ligand is ethylene diamine. We mentioned that a few minutes ago. So again, the cation is complex. Our counter ion is -2. Cation is a charge of +2. But we have now not all of our ligands are neutral. Ethylene diamine is neutral, but each of our chloroligands has a charge of -1. So the charge of our metal ion, we can say, is the total charge, which is +2, minus the 2 times our -1 from our chloroligands. So the charge of our metal is +4. So the oxidation state of platinum is +4. And when we're naming this, chloro comes before ethylene diamine alphabetically. So if we're going to name this, then we would just go ahead and say dichloro. Now here we use bis as a prefix for ethylene diamine. And when you use these other prefixes, you want to put the name of the ligand in parentheses. So dichloro bis ethylene diamine, platinum 4 chloride. Here's another example. First of all, notice that the complex is the anion. So when we're naming our nickel, we need to add ATE to the end. Let's first find the oxidation state of nickel. So ammonium each has a +1 charge. So overall, this is +2. So that means that this is -2. So the charge of our metal is going to be the overall charge, -2, minus the charge of our ligands. So water is neutral, so this has a charge of 0. This is a ligand we haven't seen before. This is called oxalate. This is what oxalate looks like. So each oxalate has a charge of -2. So overall, this is -4, or we could say 2 times -2. The charge of our metal is equal to the total charge, -2, minus 0 plus -4. So the charge of our nickel in this complex is going to be +2. So this is nickel 2. So when we're naming this, aqua comes before oxalato. Oxalato is a bidentate ligand, so we'll put that bis prefix. So this is ammonium, and then a space between our cation and our anion. Diaqua bis oxalato nickel 8. So we add that ATE because the complex ion's an anion. Nickel 8, 2. There's also some rules for writing formulas. So you write the cation before the anion. So we've been seeing a lot of formulas in all of these examples, but we just want to state explicitly what these rules are. The cation's written before the anion. The charge of the cation is balanced by the charge of the anion. So overall, the coordination compound is neutral. And then for the complex ion, ligands are written in alphabetical order, and the formula of the whole ion, the whole complex ion specifically, is placed in brackets. And then your counter ions are written outside the brackets. So let's try this example really quickly. Okay, we've got potassium. We don't know how many potassiums we need, but I'm just going to write that down. And then we have aqua tribromo dichlorocobaltate 2. So I guess I should have mentioned this, but I mentioned that the ligands are written in alphabetical order, but your metal comes first. So we're going to put our brackets, and then I'm going to write cobalt. I've got water, and then 3 bromo ligands, 2 chloro ligands. We need to figure out what the charge of this overall complex ion is, because we need to figure out how many potassiums we need to balance it. So we know that's cobalt 2. So let's say that the overall charge, and we're talking just about the complex ion, is going to be equal to the charge of the metal plus the charge of all the ligands. So we have +2 for the cobalt, 0 for the water, 3 times -1 for the bromo, and then 2 times -1 for the chloro. Overall, we get -3. So this has a charge of -3. So that means that we need 3 potassiums to balance this charge because each potassium has a +1 oxidation state. Okay, so just some conclusions. Having a standard system for nomenclature is incredibly important as we're having these discussions because it allows us to communicate the structures that we're talking about.